Section 1.5, analyzing graphs of functions. So taking some of the ideas we've been looking at over the last couple of sections and then applying them specifically to the visual of graphs. So talking about the graphs of these functions and some equations also. Nice thing about graphs is they have a very easy visual check to see whether they are functions or not, the vertical line test. You draw a vertical line through the graph at any point. And if that vertical line hits the graph more than once, then it's not a function. So right here, we got vertical lines clearly hitting that curve twice, so that is not a function. Okay, over here, wherever you draw that vertical line, each vertical line only hits the graph once. That means each input, because each vertical line represents an x value, each input only hits the curve once, one output. Over here, drawing vertical lines is hitting, look at these vertical lines, not hitting the graph at all. But that's okay. It says that it can only hit it a maximum of one time. It doesn't hit it at all, not a problem. So that is a function as well. Now we want to talk about the domain and range of each of these. Now when you have the visual, you don't have the equation like we looked at in the last section. So you got to have a bit of a different approach. You got to have a visual approach. What I like to do is I like to look at the shadows that the function casts on each axis. So to get the domain, the x values, imagine there's a light up here and it's shining down on the graph. And wherever the graph is, it casts a shadow below it. So the graph is casting a shadow on the x-axis, right there, where I'm drawing that blue. Okay, the light shining down, it's hitting the curve is casting a shadow. So we see that the shadow starts at x equals 0 and then goes over to the right towards x approaching infinity. So our domain is the set where x is an element of the real number system, with the exception that x is greater than or equal to 0. Starting at 0, and it goes to the right. Now to do the range, same kind of idea. Imagine that there is a light over here shining on that curve. And wherever that light hits the curve is going to cast a shadow behind it. So we see the light coming this way, it would put a shadow on the y-axis there, and it would put a shadow on the y-axis there, because these kind of continue going up. Remember, if the curve goes to the edge of the window, you assume that it continues going in that manner. So it will continue going up to the right, it will continue going down to the right. So the shadow will continue to cast over the entire y-axis. So our range is the set, now be careful, where y is an element of the real number system. Domain is x, range is y. There are no exceptions, so we close the set. So kind of looking at it that way, thinking about a shadow being cast on the axis, and then your function notation should reflect where those shadows occur. Now, a pretty important thing that we look at when we look at function analysis, this comes up in calculus all the time. We're always interested in zeros, okay, zeros of a function. Well, the nice thing is we already kind of know about zeros of a function. The zero of a function is all the x values where f of x equals 0. Well, remember, f of x, that's function notation for y. Okay? And we've already looked at a certain type of problem where y equals 0. Okay, we looked at that back in section 1.2, intercepts of equations. So y equals 0, zeros and x intercepts. They're the same thing. They are where a curve crosses the x-axis and the y value equals 0. So to solve zeros of a function, you're going to take f of x, replace it with 0, and then solve using your handy-dandy algebra skills. We have a quadratic. It's very possible this quadratic is easily factorable. So 2 sets of parentheses. The first x values you need to multiply to 3x squared, so that's 3x and x. And now you got to think to yourself, okay, 2 numbers that multiply to negative 10. So one of them is going to be positive, one of them is going to be negative. But when you do the outside values multiplied together, the inside values multiplied together, they have to add up to positive 1. Okay? So I'm thinking we're going to need a positive 2 and a negative 5. Because the 3 and 2 multiplied together give you 6x. Negative 5 and x gives you negative 5x. Negative 5x, positive 6x gives you positive 1. Negative 5 times 2 gives you the negative 10. So, 0 product property now, 3x minus 5 equals 0. That means x could be 5/3. 0 product property, x plus 2 equals 0. That means x is going to be negative 2. And depending on the kind of problem you have, you need to solve it appropriately. So a square root function, a good idea is probably going to be to square first. Okay? Over here with a rational function, think about when a fraction would equal 0. Okay, think about fractions that equal 0. What do they all have in common? What number's in the top? Okay, you can start there to solve that one. And another big part of function analysis, graph analysis, is looking at behaviors. Now, the behavior of a function can be increasing, decreasing, or constant. And what you do is it's like reading a book. You're always going left to right. So as you go along the function left to right, what are you doing? Are you going up or down? Well, as I go left to right, looks like I am going up. So this function is increasing. Now we're going to use what's called interval notation. Interval notation. Now it's going to look a little like something else you've seen before. It's going to look like ordered pairs. This is where context is important. What are we talking about? And then the notation serves what we are talking about. So this function's increasing from all the way over here off the graph, from negative infinity all the way over to x equals negative 1. Okay? The values that you put in here are x values, because this right here tells you about the y values. It's increasing. Y values are going up. Well, for what x values are the y values going up? For these x values, from negative infinity to negative 1. And then we kind of get over that hump and we start going down, 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 down from negative 1, x equals negative 1, to positive 1, x equals positive 1. On that interval, the y values are decreasing. So we are decreasing from x equals negative 1 to positive 1. We bottom out. And as we go left to right, we see we start going up again. So, put a little comma, from negative 1 to positive infinity. Now you should see some nice transitions here. Negative 1 to negative 1, 1 to positive 1. All right? It's increasing, it's decreasing, it's increasing. You should see that in your intervals as well.